Okay, moving on. This is part 3 of our section 8.1 video. And I'd like to not draw a line on the screen, but I'd like to grab this little note over here and show you that this ends up being a consistent dependent system. I want you to flip back to page 1 of your notes to look up what that means as I go ahead and get started by drawing my table of coefficients and constants. Okay, folks, here's my table of coefficients and constants. Remember that this column represents the coefficients for x, this column the coefficients for y, and this column the coefficients for z. And these are my constants. I'm going to call this row 1, row 2, and row 3. Alright, the first thing I'm going to do is I'm going to, if you recall from the previous video, trying to get 1s down this column and 0s in this column. So the first thing I'm going to do is I'm going to multiply -2 times row 1 and add that to row 2. Row 1 will remain unchanged. 2, -3, 1, -5. So multiplying -2 times 2 gives me -4. When I add that to 4, I get 0. -2 times -3 gives me 6. 6 minus 4 gives me 2. -2 times 1 plus 4 gives me 2. And -2 times -5 is positive 10 plus 13 gives me 23. Okay, let's go ahead and work on row 3 at the same time. I'm going to do -3 times row 1 plus row 3. And here's what my new row 3 will be. And I'm going to let you go ahead and pause the video and confirm that for yourself, that those are the correct values for row 3. What I'd really like somebody to do who's watching this video is remind me in class to show you a way to help you with the calculations for each of these row coefficients. I'm going to be honest with you. You're doing a lot of multiplication and addition of different numbers. There's opportunities for a lot of mistakes here. I want to try to show you a way to save some of these values in your calculator so you can use your calculator efficiently to do some of these calculations. I know they're pretty easy, but you're still doing so many of them, there's a good chance you're going to make a mistake. Okay, what next? Well, let's go ahead and multiply. Let's try to get rid of this 4. And in order to do that, I'm going to do -2 times row 2 plus row 3. Row 1 and 2 are going to remain unchanged. I'm going to go ahead and fill those in right now. Okay, so trying to get rid of this 4 and turn that into a 0, I'm going to do -2 times row 2 plus row 3. That's going to give me a 0 here. -2 times -2 is -4. You add that to 4, you get a 0 here. -2 times -2 is -4. You add that to 4, you get a 0 here. And last but not least, I'm going to do -2 times 23 and add that to 46. The problem with that is -2 times 23 is -46. And when you add that to 46, you get 0. Okay, now we're going to talk in just a minute about what this means. But first, I want to work on getting 1s in this along this diagonal. In order to do that, I need to multiply row 1 by 1/2 and row 2 by 1/2. I'm going to go ahead and pause the video and do that for you now. Okay, so I've gone ahead and multiplied row 1 and 2 by 1/2, and that gives me my 1s down the diagonal, at least until this last position, and then I have my 0s in the corner. So what we really need to talk about is this little feature right here. I have this whole row of 0s. It's basically saying 0x plus 0y plus 0z equals 0. And that is a true statement. That's why this system is a consistent dependent system. If you go back and look at our notes, that basically means we have infinitely many solutions. at this point in time, we need to parameterize our solution. Okay, so what I'm going to do is I'm going to, at this point, say, well, let me go ahead and write out what each of these lines represents. The top line represents the following equation. X minus 3/2 y plus 1/2 z equals negative 5/2. And what I'm doing now is converting this table of coefficients and constants into the triangular form of the system. The second row is represented by y plus z equals 23/2. And the last one is 0 equals 0. So there's nothing I can do. We can go ahead and write that, 0 equals 0, but we can't just leave it like that. So what we're going to do is we're going to say this. We're going to say let the variable z equal the parameter t. And what I'm going to do is I'm going to solve for y and x in terms of the parameter t. Let's first look at y. So for y, I'm going to rearrange this equation and write it as y equals 23/2 minus z. Well, we've already said that z, that is a minus there, not a plus. We've already said that z equals t, so I have 23/2 minus t. And that's y. Now t can be any number we want. If we want t to be 5, then we plug 5 in and we do 23/2 minus 5. If we want t to be 100, then we plug 100 in and do 23/2 minus 100. I'm now going to do the same thing for x. It's going to require a little more work though, because I have both y and z that I have to work with. I'm going to go ahead and do that for you right here. So I've rewritten my equation as x equals negative 5/2 plus 3/2 y minus 1/2 z. The next thing I did is I plugged in my expression for y right here and my expression for z, which is just t, right here. Oh, folks, that's a mistake. That should be a t. Let's fix that. That should be a t. So the only thing that should be in this equation for x are numbers and the parameter t. Okay, so let's see if there's anything we can simplify here. Well, we've got negative 5/2, and then we have 3/2 times 23/2. That's 69/4. Then we have 3/2 times negative t, so that's negative 3t/2. And then minus 1/2 t, or minus t/2. So let's see if I can simplify any of this. 5/2, negative 5/2 is really like, I call that negative 10/4. So I can rewrite negative 5/2 as negative 10/4. And the reason why I did that is because that gives me a common denominator with 69/4. And I can now say that x equals 59/4. And then I have minus 3/2 t, or minus 3t/2, minus t/2. That's minus 4t/2, or plain old minus 2t. Alright, so folks, we are actually done. We have solved this consistent dependent system, and our solution looks like this. Now it requires the parameter t, but it's still a solution. The solution is 59/4 minus 2t for x, and then y is 23/2 minus t, and then z is t. So in order to find an exact solution, we would have to pick a value for t, like 5 or 7 or negative 15 or 11/7 or whatever your favorite value is, or whatever value of t you'd like to pick. And you plug that in to each of these expressions to find out what x, y, and z will be. Okay, folks, that's it for this example. I'm going to go ahead and move into another video for our third example, part 2, question 2, part C from the notes.